Now I hear other speakers saying hi. I guess it's time to start. Hi, everybody. How's it going? Having a good conference so far? I guess it's getting down to the end. There's only a few rounds of sessions left, right? Well, thank you all for coming to learn about web authentication and FIDO and making authentication more secure, because what's more exciting than that, especially on Friday? So before I get into the real content, let me tell you a little bit about myself, the person on stage up here. Hi, I'm Jen. I'm a security advocate at Google, and I work on cloud platform. And in this role, what I get to do is spend my time doing research around, mostly around low-hanging fruit for helping software developers write more secure software and deploy it in more secure ways. And come to events like this and get to talk to you all about it, run workshops, give talks, things like that. And another half of my job is taking feedback from all of you and working with my engineering teams to make our products better and making it easier to make right decisions around security. So I love hearing from all of you. If you have any feedback, comments, questions, complaints about Cloud Platform or anything like that, I love to hear from you. Please feel free to reach out to me. The easiest way to get my attention is probably a direct message on Twitter. I'm miming codes. Or if you'd like to contact me via another means, there's jen.run will forward to my homepage, and there's a bunch of links at the bottom to different social channels if you prefer. But enough about me. Let me take this opportunity to ask all of you some questions, since we have a nice, intimate audience. How many of you are already using web authentication or FIDO security keys yourself? Oh, only a few people. Okay, great, great. Hopefully I'll convince more of you to start using them. How many of you have been involved in a phishing incident at some point in your tech career? Either yourself, I know no one want to admit that, or cleaning up from someone else at your organization. Pretty painful, isn't it? All right, well, a couple more. How many of you have an open source project, like on GitHub or GitLab, that other people use in production? Wouldn't it be a bummer if someone compromised that account and like hid a little innocuous looking commit in there that had some malware? That would be a bummer. But it's okay, because you'll be safer after today. So let's talk a little bit about authentication. Let's set kind of some grounding and talk about authentication, which can kind of get people a little excited sometimes. Opinions come out, but let's take a look at it from kind of a threat modeling perspective. So this is the state of the art of authentication as of like the 1960s and 70s, and maybe even a little further back. Login and password. At the time of account creation, you specify a secret, and then you use that secret from your memory to identify yourself in the future. The secret shared between your brain and a server somewhere else, a different computer. And passwords are great, kinda, although they won't seem to die. One of the reasons is just how easy they are to deploy. If you have a way for someone to express their login, their identity, they probably have a way to express their password too, which is why it's the first thing we're always going to kind of deploy in a lot of situations. But even way back in the day, we started identifying problems with passwords. We wanted passwords that would help people uniquely identify themselves. But they picked things that were easy for them to remember, like these. These were super common passwords way back in the day, and they're also some of the most common passwords roughly today. They're still, these are from 2016 and 2017, but these passwords are both still in the top 5, which we can get from password breaches. So people are still using these kinds of passwords. But even years ago, we came up, and the threat that we're kind of, we want to prevent with this situation is guessing. We don't want people to use passwords like password or 1, 2, 3, 4, 5, 6, because we're afraid that someone will guess that password. At least this was the common threat we were concerned about long ago. And in this situation, we have a user logging in with their login and their very simple password. And their login is not a secret at all. It might be their email address or their name, some derivation of public identity about them. So what an attacker can do is find out their login and then guess their password and get access to the service. But it's okay, because even way back in the day, we figured out ways to try and reduce and mitigate this risk. We came up with things that were easy to implement in code that hopefully convinced people and guided them towards better passwords that were harder to brute force. Oh, we also told people to never write passwords down, which It's kind of a funny thing because you wouldn't want someone searching their desk and physically gaining access to their office to then access their system because we were dealing with different threats back then. And we hoped that people would come up with passwords like this password I got out of a password manager recently. Lots of randomness in here, lots of entropy. Very difficult for somebody to just sit down at my desk and guess. But the code we implemented was only so sophisticated, and people came up with their own ways of working around it. I mean, how many of you have added like a capital letter and an exclamation mark to a password to make it pass one of these filters? A lot of us have. Yeah, a lot of us. I have too. It turns out that these maybe help the guessing a little bit. But the truth is, even if people used very secure passwords, they would have trouble remembering these. So they started reusing them across multiple providers. And our threat changed a little bit. They wouldn't use it in just one site. They'd use it in 10 sites, all their sites. They'd have a high security password, a low security password, maybe a few classes of passwords. But times changed, the internet became a thing, and we ended up with more accounts than ever, and some of those accounts ended up in situations that got breached. And now you can go out and you can go buy from people in the dark web databases of literally billions of credentials of login and password combinations, which is crazy. And these are usually like glommed together from multiple breaches across many organizations. So you end up in a situation where credential stuffing is a much bigger risk than password brute force guessing these days. Because people have followed our advice and come up with an amazingly secure password and reused it everywhere, they use it in a service. That service gets breached. Maybe that service used plain text password storage, which would be awful, or maybe somebody spent a lot of time reversing those passwords from those hashes. Either way, hackers bought that information, and then they use it in a whole bunch of other services. And even though like company XYZ may have like gotten the user to change that password, that user may have been using the same password in an email account or a frequent flyer account they forgot about a long time ago, and attackers can do all sorts of bad hijinks with it. And ironically, if the users had just not followed our advice and written that down in a notebook that they kept with them all the time, credential stuffing would be much smaller of a threat. Yeah. But it's okay, because we had another way to mitigate that. We had a technology called one-time passwords. One-time passwords are great. The idea behind it is, in addition to the password, you ask the user for a one-time code that is delivered to them by a secure way, either like sent to them by an SMS, and thereby you're guaranteeing that like they're holding that phone that has that phone number on it, which is pretty good. Or maybe you shared a secret ahead of time, and you can generate new one-time passwords together over time using cryptography. Or maybe you carry around a device that was sent by the provider. Like we've had these for a long time. I remember back in the day, you just have a big fistful of these, one for each account. And these are great, but they actually don't protect against a new rising, I guess an old, but rising in sophistication threat. So one-time passwords are great. They protect against credential stuffing. They protect against weak passwords, but they actually don't help that much against contemporary phishing attacks. In a phishing attack, we have our user wanting to log into the service, but instead, a hacker spins up a fake service that closely resembles the real service. And then they convince the user, either through social engineering, through targeted emails, or just like through a scattershot approach of sending out thousands and thousands of untargeted emails. Anyway, they get some number of users to log into that service. And even if the user is using a one-time password, the attacker can still take that information and forward it to the real service and use automation to like disable one-time passwords and change passwords and cause all sorts of chaos. So although one-time passwords make it a little harder to do the phishing attack, phishing, especially sophisticated phishing, is still a really big threat. One-time passwords don't help that much. And the fundamental issue behind it, the fundamental challenge we're facing, is that we don't have some telepathic way of communicating our shared secret to the server. We have to go through a user interface. And whenever we have to use the user interface, us as humans have to judge whether that's real, and that's a lot of cognitive load, especially in a time where we might have other stressors, other things on our mind. Phishing attacks are surprisingly effective, even against security engineers sometimes. If you manage to catch the person at a time when they're very weak, or you manage to find a way to, develop a sophisticated enough fake page that they don't guess it. So what we need to do to solve this problem is we need a way to reduce the cognitive load on our users. We need to make it easier for them to make the right decisions. And we can do that with technology. And that's where Webauthn and FIDO keys come in. They reduce the amount of cognitive load our users have to do. They reduce the amount of judgment calls they have to make so that we can securely authenticate them. And it also protects against a bunch of other things too. So let's spend the rest of the time talking about that. I'm going to spend a little bit of time talking about the solution in a very abstract sense, and then work our way up towards concreteness. I'm going to talk about the protocol a little bit. And then in the most concrete form, I'm going to talk about how you can use these to protect yourself and protect your open source code, protect your email accounts, and then finally, how you can add support to your software so that your users can protect themselves too. And then you don't have to deal with a phishing incident from a customer or a colleague or something like that. So first, in the most abstract sense, let's talk about how math can help save us. Because math is awesome, right? So it all comes back to public key cryptography. Rather than sharing a single secret, we're going to use public key cryptography to help us authenticate users. And just to kind of recap, because I'm sure we're all familiar with public key cryptography, but the gist of how it works is, because of some oddities of mathematics, we can generate these keys that come in pairs. A private key, a public key, or in this case, a yellow key and a green key. And these keys have a special property. Is when you take a message and you encode it with one key, it is only decodable with the other key. And the algorithms we use also are bidirectional. So if I encode something with the other key, the green key, I can only read it if I have the yellow key. Which is great and all. It allows us, obviously it allows us to securely transport information. But how does this help us with authentication? Well, let's go through that. There's going to be kind of a two-phase process. First, we're going to have to do registration. And this is going to come up over and over again throughout the rest of the talk. And then once we've successfully registered, then we're going to do authentication. So let's talk about how public key cryptography, how we use registration and then authentication to be able to identify people later. So here's kind of the most simple version of the registration dance. We have a user, and the user has a service they want to use. The user generates a key pair, a green key and a yellow key. And then they take one of those keys and decide that it's the public key, and then they transmit it to the server, hopefully over a secure channel. And the server remembers that green key. So great, we've now registered. We have given one key to the server, and we kept one key. The yellow key we're going to keep private and keep that secret, because that's what the server is going to use to identify us. So then later when we authenticate, what the server does is it takes the green key, recalls it, and remembers it, it looks up the key for that user, and then it generates some random string of stuff, which it calls a challenge. It takes that challenge, sends it back over the wire to our user. Our user takes that challenge, encodes it using their private key, transmits it back over to the server, and then the server can use the green key to unlock the green lock, decode the message, and verify that the challenge is the same, that the signature matches the challenge it sent. And what this does is it guarantees that we are the same user as before, or more specifically, that we are the user that has the yellow key. And if the user was successful at keeping that yellow key private, we've now successfully authenticated the user without having to transmit that shared secret back and forth. Yay, success. But of course, the devil's in the details. We'll be getting more into that. It's a little more complex than just this. So let's get into some of those details. So to actually make this work in reality, we're going to need a couple of different things. We're going to need some hardware, because doing cryptography on paper, although possible, is very, very difficult and error-prone. So we're going to need some hardware to actually do the cryptography for us. And we're going to need a protocol so that we can communicate that securely from our cryptography hardware out to the server and back and forth. We need a way to communicate that back and forth. So first, let's spend a little bit of time talking about the hardware. Hardware comes in many different flavors. The most common one you're going to see, which has been around for a little bit longer, is these tiny little dongles, little USB dongles that you plug into a USB port, maybe leave it in there, And then they expose themselves to the computer as a human interface device, so it can transmit information to the computer. They can also use near-field communication for communicating with mobile phones, just like tap to pay, except it's tap to do cryptographic stuff. And if all else fails, we always have the Bluetooth transport, which is not as ideal. It's a little bit clunky, but it's the only option that works on iOS today. But one of the cool things that's starting to emerge is we don't have to carry around those dongles necessarily, because now we all have hardware either on our mobile phones or our laptops. They have these cool secure hardware enclaves. Like they have special reserved places of hardware that are especially hardened for the purpose of doing cryptography. So that even if someone gets malware on the computer, it's going to be very difficult for them to extract information from that secure hardware enclave. And these also have the added bonus of biometric security or some other way of unlocking that secure hardware enclave so that I can do that signature. And what's cool about Webauthn is it supports these as well. So although the physical security keys are always probably going to be the most secure because it's very difficult. Once I compromise the computer, then I have to find another way to compromise the keys itself to get in. And the hardware in these is very simple and easier to secure. I think that these are going to be a lot easier. The platform authenticators are going to be much easier to roll out at organizations. So yay! Way to make it easier. So now that we have hardware that can do the cryptography, now we need a protocol. We need a way to communicate that back and forth. And this is where you kind of get hit by the jargon bomb if you're researching this. There's a lot of acronyms that come involved here. There's FIDO, which is Fast Identity Online, the organization. There's Webauthn, there's U2F, there's CTAP. There's so many different acronyms. So let's try and put some of these in some context. So FIDO stands for Fast Identity Online. It is both the organization of many people from different companies and different standards. This is a standards body, essentially. And they have protocols, the FIDO protocols. FIDO 2 is the name of the overarching set of protocols that make this all possible. So Fast Identity Online 2, if you search for that, you'll find like a very wide description. It's the big bucket, the umbrella term, I guess. In FIDO 2, we have our user, and they have a server that they want to access. Within the specs, it's always going to be called a relying party. You're going to see relying party or RP come up all the time. It just means the server that's doing the authentication. They have authenticators. These are either going to be removable authenticators, which is basically a way to describe those security dongles that are USB or NFC. And there's also platform authenticators, which in the spec is also referred to as built-in sometimes. When you're communicating between the authenticator and the computer or the user, you're using a protocol called CTAP, which is a low-level, essentially wire protocol. There's two versions of CTAP right now. There's CTAP 1, which is also a subset of the older U2F protocol. So if you find yourself like buying one of those USB devices and it advertises U2F, it's probably using the CTAP 1 protocol. There's a newer CTAP 2 protocol, which adds a few more bells and whistles. It adds a little bit more persistence on the key that's required. And it uses a slightly more convenient encoding format, but they're both very secure. So your CTAP 1 U2F keys are still awesome and reverse compatible with the newer specification. And then finally, Webauthn. Webauthn is the W3C standard that defines the interaction between the relying party, relying party and the user on their device. And the reason you're going to see this come up a lot is because if you're rolling this out in your software, all of the code you're going to write is going to be dealing with the Webauthn protocol. That's the standard you're going to have to look at. Those are the libraries you want to use. Unless you're building your own security key from scratch, you probably don't need to worry too much about the details of the CTAP protocol being used. But if you want to, you totally can. It's also in a FIDO standard doc. A little bit harder reading, though. OK, so there. Hopefully that dispels some of the jargon bomb. Webauthn seems to be the emerging word that's attached to the newer devices. FIDO 2 has not caught on quite as much, but you'll see multiple things in a lot of on a security key advertisement and stuff. Okay, so we have the hardware, we have the protocol. Let's first help me achieve my #1 goal, which is we're the developers out there. We're the most technical people in a lot of people's lives. We should be setting the example by doing strong authentication. So I'm going to slow down the pace a little bit, and I'm going to show you in painful detail how you can use it to protect yourself. So the first thing is you need to get an authenticator. There are a whole bunch of different vendors for authenticators. If you just search like the web, you can probably find 200 or 300 different authenticators now. Here are a few different manufacturers that I think are kind of cool. The first one that comes to mind, one of the leaders in the space, is Yubico. They make keys that support U2F, FIDO, CTAP1, and Webauthn. They also have a lot of other bells and whistles. So if you really want to get into the space and you want to do like all the smart card stuff and you want to like do GPG signing and like use the smart card SSH stuff to do your SSH keys, the YubiKeys are great for that. There's also Solo Keys, which is a fully open source one, which I think is pretty awesome. And they're also the cheapest way to get a USB-C key right now. So if you want to buy a whole bunch of USB-C keys to roll out to your organization, Solo Keys are probably the cheapest way to do it. And Google, we have our own kit, which comes with 2 different authenticators. And the idea here is you have your backup that comes with it. And we also include a Bluetooth key so that you can use it on all platforms, including iOS. So they all work pretty much everywhere, with the exception of a couple sites that are Yubico-specific stuff. But they generally work pretty much everywhere. So you need to get a key. Also, since you're in the conference today, if you stop by the Google Cloud Platform booth after my talk, I will have keys, Solo Keys to give away, if you promise to use them. OK, so now you've gotten your hands on some hardware. Next, you want to register it on important sites. And now I'm going to drag you through registration and authentication on 2 providers. First is GitHub, because a lot of us have open source software. I don't want supply chain attacks becoming more common. We should all be using multi-factor auth and strong authentication on our GitHubs. So here's a little screencast. In the corner, you can see a little camera pointed at a security key. And you can see that I'm logged into GitHub right now. So you have a security key, and you want to set it up on GitHub. You log in. You go to Settings. Go over to Security. On GitHub, you have to have already set up 2-factor authentication to add a security key. So I've already done this ahead of time. So set up 2-factor authentication. If you haven't, please do that right away. That will cause a security key option to appear. You go over there, you tap Add, and it'll bring you past a bunch of warnings about not getting yourself locked out. You can just ignore those, scroll right past them. And register a new device. You want to give it a name, because GitHub is awesome and supports multiple security keys for each account. Click Add, and then it will do the registration dance. The key will start blinking or some other indication. You tap it, and it's registered. Yay! OK, you are now protected. At this point, if you ignore those warnings, you want to go read them and set up a backup method of authentication or register a second key. But when it's time to log in, you'll log in with your username, with your password, and you get an extra step, which is insert your security key. If you lost it, you can go to a fallback method. But it'll start blinking. You tap the key, and you're logged in. Yay! And you're super protected. OK, one more. Google accounts. Because think of email accounts are something you definitely want to protect. And a lot of different email providers support it now. And that's because a lot of your password resets, your backup authentication for a whole bunch of services you use probably relies on your email being secure. So assuming some of you use Gmail, let's take a look at protecting your Google account. This would also work if you're a GCP account user. You definitely want to protect those accounts that have super admin permissions everywhere. So we're going to go click on security. And what's cool about this is we got to put in our password. And this is just to protect you from people coming up and registering a security key with your account when you step away from your desk. But anyway, when you go to set up 2-factor, it will try and steer you towards using a phone, because that's the most convenient way for a lot of people. But there's a little drop down, and you can pick security key. And you can actually do this as your only form of 2-factor authentication. So if you want to be super secure, you can just use security keys. And it's going to guide you through the same process. It'll start blinking. Yay. You give it a handle. I'm going to call it Han, because it's a solo key. And Google supports multiple security keys. So this is a point where you might want to add an additional security key as a backup, and then put it somewhere safe, or get your backup codes or your secondary, your backup authentication method. And now that we're registered, we can go ahead and log out and verify, give the authentication a quick check. So let's go ahead and sign out. Let's clear that stuff from it to make sure it asks us for the security key. And let's log in again to the test account. We log in with our username and password. We get this prompt from the browser to go tap our security key. We tap it, and yay, we're authenticated. And if you're using like a Google organization, like if you use G Suite or Cloud Identity for Cloud Platform, you can actually set up policies where you require a subset of your users, either the users that are most sensitive or have access to the most accounts, like the people who have access to Android signing keys. If you have a Google domain, you can actually enforce it and require them to use it, which is a great way to make sure no one's going to sign like rando apps, which would be a terrible thing. So this is kind of cool. And there are lots of other places you can use it too. And there's actually directories online. Like this one. This one's my favorite, dongleauth.info, which NitroKey has sponsored. And you can put in other stuff up there. Like if you use a different email provider like Fastmail, Fastmail supports it. Or if you want to see the sorry state of investing sites, you can see that pretty much nobody supports it, which makes me sad, except for Vanguard. But their implementation has some challenges. But hey, it exists. So you can go and check all of your favorite sites, all of the places you have accounts, go through your password manager, pick all those domains, see which ones have supported and add it. But notable ones are like Twitter, Facebook. Yeah, those are things you might want to add security. AWS is another one, cloud computing. Although theirs also only supports one security key. Hopefully they change it. Cool. OK, let's go back to the slide. So yeah, you go and you add it to all your services. Yay! You're super protected now. So now you're protected. You feel safe. Everyone around you at your organization or all your customers are like, hey, I see you using those security keys. I want to be protected too. Or more likely, you decide to enforce it upon them somehow. Let's talk about adding support to your software. So what I really wanted to do was come up here and like crank out like a 10-minute live code demo. I did my best. I did a bunch of implementations with like several different client libraries. We're not there yet. So the best implementation I came up with was using the Duo, or the smallest implementation, was using Duo Labs' Python client library. I got down to an implementation that resulted in a patch file of about 850 lines of code. So not quite live code ready yet. But instead, let me give you some advice from having tried this with a whole bunch of different client libraries. The first one is use a client library. You're dealing with cryptography, especially on the server side. Don't try and roll it yourself. Use a client library. The other thing is that the client libraries are kind of new because the Webauthn protocol is been moving through different levels of specification. So these libraries are all pretty young. So whenever you use cryptography libraries in production, proceed with caution. Most of these haven't reached 1.0 yet. Make sure you give them significant amounts of review and take your time. So make sure you set aside time to do it. But this list is from webauthn.io, which is a website maintained by Duo Labs, I believe. And it is a great site that links to a curated list of client libraries, which is a pretty good list of client libraries. So that's a good place to start your search for client libraries that match your infrastructure and your code best. And then once you have a client library, it's time to start implementing stuff. There's a wonderful site out there also maintained by Duo Labs that is just so awesome that rather than like re-implement the stuff on my own slides, I'm just going to drag you through the site. This is webauthn.guide. And it has not only does it have beautiful illustrations, it is probably the most succinct explanation of Webauthn I've seen so far. So let's scroll past all the pretty graphics and let's talk about registration and authentication. So here's a little cartoon that kind of describes the process, similar to the stuff we showed earlier, where you have either a new account, although more commonly, you're probably going to have an existing account that's already authenticated, and you want to add a key to it. Although for some reason, most of the demos assume you're doing it at time of account creation. I don't think that's realistic. But just whenever you see new account in a demo or a documentation, just assume that's like adding a key to an existing account. But essentially what you're going to do is send a request out to the user, and then they're going to send a public key, and then you're going to do a wonderful process to verify that. So when the user says they want to register a key, you're going to call this method, this part of your browser API, navigator.credentials.create. And here it looks all cute and nice. It's actually kind of a little bit, this API's got some edges. It's not as simple as just passing in a single parameter, because we want flexibility. And this is actually what it looks like when you call the method. There's this big old blob of configuration information that you're sending up to the browser so the browser can make that call successfully. And there's a few different things you're packing into there. The first one is that challenge. Even during registration, you want to do a challenge so that you can verify that the user actually has that private key. But one of the things that's weird about the challenge is the challenge is passed to the API. You can't just give it a base64 encoded string or a string or something nice like that. You have to give it an array of integers, I guess because it makes it easier to communicate to the key. So you want to encode that. So you're going to be doing a little munging. You're going to include information on the relying party. Sorry. Your name is actually required. You have to give a human readable name. This shows up on the dialog in the browser. And then you give an ID, which has to match the domain name, the origin from which this came. So if you sent this up via JavaScript or you burned it into the page, it's going to have to match whatever's on the browser at that time. And it'll also have to be stable because you're going to use it during authentication. You also have to tell the user a little bit about themselves. You have to give an ID as required field. And in all the browsers, the spec is a little bit loose here, but from Firefox and Chromium-based browsers that I played with, it generally has to be an array of integers. But it's if you use this kind of encoding, it seems to only work if you give it alphanumeric characters. Latin alphabet. If you throw it at signs or stuff outside, extended character sets, it seems to get kind of cranky. So you have an ID. I guess typically this is going to be a numeric ID from your database. Name is actually their login. It's not actually their name. So whatever the login they use, either an email address or their login identifier. And then you're actually required to send a display name up with the user. You can use an email here if you don't have a display name in your account. And then one thing that's kind of funny is the spec talks a lot about an icon. So the keys, like a little bit of trivia, the keys are encouraged to support storing up to 128 bytes of profile icon information for the users. But I'm not exactly sure why. I need to figure out who got that added to the spec and ask them. But it's technically optional, although most of the client libraries just flatten it down to an empty string. Empty strings work here. You need to tell it what different algorithms you can support, and you have this like encoding you have to use for the algorithms. These are the different cryptographic algorithms you want to support. And if we go to the spec, we can actually see there's 3 different algorithms that are required to be supported by the keys, which is what everyone supports today. Let's find those. So the easiest thing to pass in is just -7, -257, and -37 if you don't care. That'll pretty much guarantee it's going to work for all the keys that are out there today. If there are keys that support other encryption algorithms, I haven't found them, and I buy all the ones I can find. I haven't gotten any key to respond to anything but those 3, but they all respond to all 3. So what else are we setting up? Authenticator selection, you can specify whether you want to use a built-in authenticator or cross-platform, one of those dongles. You can leave. This is optional. I typically don't care what authenticator people are using, so you can leave this out entirely. Timeout is technically optional, but it's really not. The default timeout in Chromium-based browsers is super short. Like I don't know if it's a second or less than a second, but it seems to happen pretty much instantly. So specify a timeout. And that's just how long they have to hit the button on the key before it like says, hey, you ran out of time. Then attestation. So you have a few options here. Direct will give you detailed information about the key they've inserted, which does compromise the user's privacy a little bit. You might be able to use it to track the user to some extent. But this is useful if you are in like an enterprise and you want to make sure that they are only using the keys you gave them. You can whitelist certain key providers, or if you want to like blacklist keys that are manufactured in a certain place or something like that, you would set this to direct and you would use that to filter the keys that people are allowed. If you set it to none, people can use any key, and for a lot of consumer-based stuff, I would just set that to none. Okay, so then you finally get all that data information up there. You munge it into the right by the integer arrays, and you send it to the method, the credentials.create, and it'll run, and it'll give you back stuff that looks like this. This is what will come back out. It'll be returned. And you get a cool bunch of data back in a convenient format of an array buffer of binary data. I guess it comes right off the key and right back into your code, which is great because you have to communicate that back to the server, and it's always fun to communicate random binary data back to the server. So generally what you're going to do is you're going to base64 encode this, send it back to the server somehow, either by like a combination, either base64 encoding it and sending it over like a JavaScript request, or you can actually bake it into a form and submit it. The spec doesn't actually care how you get it back to the server. You just got to get it back somehow. Then, when you're back on the server, there are a couple chunks of information that are going to come back out. The challenge is going to come back. You want to verify that challenge matches the challenge you sent. The origin, you want to make sure that this didn't change in flight somehow, that it matches your domain name. And actually, the full process is in the spec as a 19-point procedure, which is why you want to use a client library, because it makes it like a one-step process. You're going to spend some time decoding it because you got back like base64 encoded stuff. You're going to decode it, and then at the end of the day, you end up with a bunch of cool information that you want to save some of. The notable information that's going to come back that you want to keep is a credential ID, and this is going to be a real long string which identifies the key. So it's actually the combination of your information, your origin, and the key's private key. So it's generated for each service independently. But for you, that identifier identifies that key. It'll be stable. So when you later want to recall that key, you want to store that. And of course, you get the public key out. You want to use that because that's the whole point, having that green key. And you get back some other information you can use to verify, like the encryption algorithm supported and stuff. And these you're required to store, but I would also recommend that if you used any interesting options up here, store all of that with the key record also. Because when you do authentication, you're going to need to recall some of that information. So like if you requested cross-platform only and all that stuff, you want to store that information up back in the database too. OK, so at this point, assuming that 19-point check being handled by your client library was successful, you now have a registered user. You can store that key. Please support multiple keys. So at this point, you can store it in a separate table or a separate object in your database. And then, yay, your user is protected. OK, so now that we have that key stored, the authentication, which is actually a little bit of a longer comic book flow, is actually a little bit easier to implement in code. At the time the user signs in, you're going to check to see if you have a key for that user. If you have a key for that user, you're going to send them some information to configure that credential GET request. They're going to sign the challenge and send it back to you. So let's see what that looks like in code. Again, you have a nice method that is deceptively simple when you just list it here. But again, you have to take some information from the server and send it back up. You have a challenge again that you generate on the server. The server needs to keep track of this, at least for the duration of the session. You send it up. It has to be converted into an array of integers again. And then allow credentials. So that credential ID, what you send up is you send up an array of all the keys. So if the user has 1 or 3 or 5 keys, you're going to send up information for each one of those keys. In the order, you can optionally specify it in the order of preference, although none of the browsers seem to do anything with that yet. So those credential IDs come back out, and you send them back up. And you can optionally specify transports at this point. I don't know why you can't specify this during registration, but you could optionally restrict them to only transmit it over NFC or USB if you want to ban Bluetooth or something like that. But there's one cool thing that is optional here, which I'm going to go over and look at the spec again, which is not in this particular, but there is another optional field called user verification. And this one's pretty cool. So it defaults to preferred, but you can actually require user verification. And what that means is it will only allow the request to work if the user verifies their identity locally in a reasonably secure way. This would either be by entering a PIN code or more likely using biometric or a password to unlock the Enclave on their platform authenticator. This is important if you want to do fully passwordless authentication. If you want to do fully passwordless authentication and make Webauthn their only authentication step, please use this because it will prevent like someone finding a key on the ground and then like doing some kind of geography attack on like everyone who submits, everyone who does open source code in a certain location. This is how you prevent that, because it will restrict it to only authenticators that can verify the identity locally. Kind of moving that password burden back to their client side. Okay, so then you send it all up, you finally call the method, and you get back another big old blob of a whole bunch of binary data, which you have to, again, base 64 encode, transmit back to the server, either by stuffing it in a form or making a JavaScript request. And the actual verification is no longer a 19-step verification. It's actually much easier for the authentication. You pretty much verify that the credentials, you verify that the challenge was signed with the public key, and then you've pretty much verified the user. The only other step here that's kind of glossed over is there's actually a counter that's embedded in the keys also. And the idea behind this is it makes it easier to detect cloned keys, which I don't know of anyone who's cloned any of the hardware keys yet, but if someone were to clone a key, each key keeps track of the number of times it's authenticated. And if you ever see the count go backwards, that means that there's a cloned key in the wild, and you should invalidate that key for that account. But one of the weird things about the spec is you don't get the initial count until you do the first authentication. So during registration, just default the count to 0, and then you'll be setting the initial count during the first authentication. It better be higher than 0, because that's what the spec requires. And then for every subsequent authentication, you want to make sure it increments a little bit. And with that, you've now added it to your software. So as you can see, we're at a point in the spec right now where, although the client libraries will take care of a lot of the server-side work, there's not a lot of opinions either in the spec or in the client libraries now about how you convey that information back and forth to the client. And you still have to do a lot of boilerplate encoding and decoding, which was most of that 800 lines of code, was basically remunging these things into like byte array formats, which is a bummer because that's kind of error-prone code. And it can end up in a situation where it works, but it might have problems. So take some time doing your implementations right now. So let's talk a few of kind of the painful realities of if you were to try and implement it today. One of the first questions that comes up all the time is, what about lost keys? Because like all of my users have a physical device. I don't want them to get locked out. That's a total pain to deal with. And this is the first thing that comes to our mind, but it's actually not as big of a problem as you would expect, because we already have a lot of workflows in place for dealing with this exact problem. Because people, like even when they're not using a physical key to authenticate, people still lose their phones they use for their one-time passwords. People still forget their passwords. We have backup methods. So it's no different for this. Rely on that backup method. If you're doing a consumer-facing service, this might be a password reset email or a key reset email. If you're at an enterprise organization, this might have them come into the help desk and say hi and verify that they look like their badge photo. Use whatever backwards or whatever fallback methods you have. And I agree that this can pose a degradation in security. This is kind of like a built-in downgrade attack. But the truth is, even if someone is using a security key for 99% of their authentications and they fall back that 1% of the time or fall back when they're using an iOS device, they're still much more protected because most of their authentications are going to happen in a situation where it's very difficult to phish them. And their spidey sense is going to be up. Like if they get a phishing attack that tells them that their security key doesn't work, like that should give them more pause. There's less cognitive load there. So lost key is not as bad of a problem as you might think. Bigger problems are that iOS support is lagging right now. I think this is kind of the biggest thorn in the side of deploying this, is that people want to authenticate their services on iOS devices. And yeah, I'm hoping that they'll kind of get on the bandwagon, especially because like so many iPhones have those platform authenticators now, potential platform authenticators. Like I really hope that this is going. And based on some of the activity in the developer preview on Safari, it looks like they're finally getting on board. So we'll have this soon. And I think that'll make rollouts a lot easier. As I said earlier, the spec is kind of young, although we've been doing stuff essentially like this for like 8 years now. The current incarnation of the spec is still kind of young, which means the client libraries are still kind of young. And as you can see, you have to do a good amount of code to get them implemented. I'm hoping we end up with some client libraries in the near future that have more opinions about transmitting information to client side and server side and are more cohesive across the flow. So you can really just kind of drop something in and know it will work pretty well. We're not quite there yet. I guess that's work that I should probably be doing. And in all of my implementations of this so far, I still have to have the spec open in another tab. which is usually another sign that this is still pretty young technology. And it's never terribly fun to have to be referring back to the spec and being like, profile icon? What is that? Is that really required? The reality is right now, if you're doing an implementation, you're still going to have to be going back to the specification, which is OK. It's not. It's actually, as specs go, it's pretty digestible. It's like I don't know, like 80 or 90 pages long, which seems bad, but like the Bluetooth spec is like 3,000 pages. So like it's actually a pretty easy to read spec as they go. So with that, I guess it's time to conclude. If I want you to remember a few things from this talk, it's that passwords and OTPs, they are not enough for a lot of kind of the modern threats we're facing. Phishing is on the rise, targeted phishing attacks are happening, and developers are starting to get targeted themselves, which is bad. We need to protect ourselves. So they're not enough, especially for us. We should all be using this technology because we have the technical expertise to be able to use it today, and we have more to protect. And also, like adding it to your software isn't too bad now. Like I know not all of you probably want to go jump and start deploying it today. But it's probably a good time to start thinking about it. Start getting ready to add this to your software. Because the more of us add it to our software, we start hitting critical mass, and then people will start demanding it more. And then the whole internet is more secure. And we've solved a really big threat right now, which would be great. It would be great if people didn't get phished anymore. I would like that a lot. So with that, thank you so much. I challenge you all now to go out, add it to your software, add it to your accounts, and we can reduce pwnage internet-wide. And here's a resource slide. If you'd like links to all the different things I linked and all that Oxy looked at, including those awesome Dual Labs things and links out to some vendors for keys, go ahead and check out the slides. There's a short link to the slides up there, too. So thank you so much. Oh, yeah, and I will be hanging out at the Cloud Platform booth. If you want a solo key, swing by. I will be handing them out while supplies last.